This is the difference between light and laser. Light is polychromatic and it has high divergence. Coming to the production of laser, we need to understand what is absorption and what is spontaneous emission. Atom has a central nucleus surrounded by electrons in various energy levels. When an electron from the ground state absorbs energy and moves to the higher state, it is known as absorption. And the electron in the excited state or the higher state is unstable, so it has to decay to a ground state. While decaying, it emits energy in the form of photons that is known as spontaneous emission. And these emitted photons will be in random direction and phase. For laser, we need stimulated emission. So what is it? An electron is in the excited state E2 and it has to decay to E1. Before the emission, if a photon passes by this electron, whose energy is equal to E2 minus E1, then the electron decays with the emission of photon, which is of the same wavelength, phase and same direction as the passing photon. This is stimulated emission, and this is what we use in laser production. In order for the stimulated emission to happen, we need atoms in the excited state. So a system where more atoms are in the excited state is known as population inversion. For population inversion to happen, we have to use an external power source. It can be optical or electrical. Now, how does amplification happen? In a state of population inversion where more atoms are in the excited state, one photon goes, then it strikes one atom, 2 photons are produced. Again, it strikes another 2 atoms, 4 are produced. Similarly, it continues as a chain reaction. So this is how amplification happens. Now coming back to the term, light amplification by stimulated emission of radiation. The components of a laser, it has an active medium, it has a pumping source, which is, we said already, it is either electrical or optical, and a resonator. Resonator has 2 mirrors. One is fully reflective and the other is partly reflective. Between the mirrors, the photons have multiple passes. They get reflected and it gets concentrated. So when the sufficient level of energy is released, that it is ejected as the laser beam. Classification of lasers according to their active medium can be gas, solid, liquid or semiconductor. The common lasers used in ophthalmology are excimer laser, which has a 193 nanometer wavelength, argon 514, double frequency ND arc 532, krypton 647, diode 810, ND arc 1064 and femtosecond 1053. You will see various applications in the coming talks. Laser delivery system can be transpupillary, transcleral or endolaser. Transpupillary can be either through slit lamp or indirect, and transcleral can be contact, non-contact, and endolaser can be usually associated, used with vitrectomy or microincision glaucoma surgery. Coming to the laser parameters which are of importance is the power, which is the amount of energy delivered in a time period, wavelength, the spatial frequency, exposure, the duration in seconds photons are emitted, spot size, the diameter of the laser, energy power into time, and fluence. That is the energy delivered per unit area in same location. That is very important in case of now the recent low fluence PDT and half fluence. That helps to minimize the collateral damage. Coming to laser therapeutic tissue interaction, there is the photochemical reaction. They are of various types: photochemical, thermal, photoablation, plasma-induced ablation, and photodisruption. We will go into each of it. So here, all these tissue interactions, the transfer energy to the tissue is between 1 and 1000 joules per centimeter square. First is photochemical interaction. Here we use a catalyst, usually a dye like a riboflavin or a vertiporphin. It reaches the tissue. Then we irradiate with a long exposure, very low power density laser, and this is absorbed by the dye present in the tissue, and the photochemical reaction occurs. Example is PDT and also collagen cross-linking in keratoconus. Now the thermal reaction, that is photocoagulation. Here the laser light is absorbed by the target tissue. The chromophores in the target tissue helps in laser absorption. That generates heat and causes denaturation of the protein. Example, laser trabeculoplasty, PRP, laser thermokeratoplasty. Depending upon the amount of energy that reaches the tissue, the thermal reaction varies. The natural chromophores are hemoglobin, which absorbs blue, green, yellow with a minimal absorption of red. So in case of vitreous hemorrhage, we use infrared leg, which is less scattered. Then xanthophyll. Xanthophyll is seen in macula and it absorbs in the wavelength 450 to 500. So whenever we do macular lasers, we aim for a wavelength more than 500 to minimize the macular damage. Melanin, which is present in iris and also in deep retinal tissue, absorbs from 400 to 580. It is excellent absorption by yellow, green, red. Now, if the temperature in the tissue reaches 60 to 100 degree, it causes photovaporization. Here what happens, the water vapor expands as a the water expands as a water vapor, causing disruption. This principle is used in cell disintegration, where we put laser incision, skin incision, also debulking of the tumors. And heat generated there causes cauterization. That can be useful in intravitreal photocautery for fibrovascular forms. The laser which exhibits photovaporization is one is carbon dioxide laser. Photoablation, here the covalent bonds are split by the photons with short time and sufficient energy and no thermal injury. Example is excimer laser. Excimer laser is or excited dimer laser. Here electrical energy stimulates argon to form dimers with fluorine gas. It has a wavelength of 193 nanometer. It is of high energy, very low tissue penetrance and great precision. So it is used in surface procedures with little thermal spread. Next is photodisruption, or it's otherwise known as photoionization. The example is ND arc laser posterior capsulotomy. Here shock waves and cavitation bubbles are produced that leads to mechanical splitting of the tissue. That is different from the newer plasma-induced ablation that is seen in femtosecond. Here electrons, the laser strikes the electrons causing ionization and acceleration. These electrons strike another two atoms, cause a further ionization. So a cascade of ionization happens and plasma is produced. And we get a clean, well-defined removal of the tissue. No thermal damage, and ultra-short pulses of femto or picoseconds are usually used. Example is creation of corneal flap, keratoplasty, then laser cataract surgery. The difference between a plasma-induced ablation and photodisruption, in plasma-induced ablation we get higher repetitions and lower energy is used. So we get a smooth surface. The interface will be smooth. Whereas in photodisruption, we have lower repetition with a higher energy. So the interface will not be as smooth as in a plasma-induced ablation. Laser output can be continuous mode or pulse mode. Continuous, we get a uniform power and continuous, whereas in pulse mode, we get concentrated energy over short periods. Can be Q-switched or mode locked. Q-switched in the range of nanoseconds and mod locking in the range of ultra-short pulses. Last, about laser safety. Laser is one we should always take precautions. Depending upon the classification, there are various classes. In class 3 and 4, it has serious eye injuries, especially class 4, where even scattered radiations are harmful. Though always the patient safety should be ensured by correct positioning. The surgeon should use filter systems. We should always check whether it is adequately working. And the safety of observers and assistants should also be taken care of by using protective goggles. Thank you.
Thank you, Dr. Sija, for that wonderful presentation.